Okay, so good evening, good morning, good afternoon, everyone. So welcome to this last session of today, or the first session of today. And it's a pleasure for me to introduce Felipe Voloch from the University of Canterbury, where it's morning, I guess, now. And he's going to talk about the part of Serge's book, or follow-up work on that, that is already on the screen. So the title of this talk is Bounding the Number of Points by Counting Tangents of the Beaten Track. So please, Felipe, go ahead.
Thank you. I hope you can see my slides now. Thank everybody for coming, especially those who are in a time zone that is perhaps not very comfortable late at night. So I want to talk about this result of mine that is in Serge's book and developments from it. But I want to take not the beaten track, but I want to go off the beaten track. So here's the abstract of my talk. Before I go off the beaten track, let me just say a couple of things about the beaten track, which is the star Voloch bound, which was already mentioned in Gabor's talk. So Gabor said a few things about that. So I'm going to be a bit brief about this. So this is a theorem that is a very flexible theorem. If you have a curve over FQ of genus G for any embedding of the curve into projective space. So that's a degree of freedom that you have. You can choose your embedding as long as it's non-degenerate, is not contained in a hyperplane. And we take the degree of this embedding. To this embedding, there's associated some numbers which are called the Frobenius orders. These are some positive, negative integers. They usually are 0, 1, up to n minus 1. When this happens, you say the system is Frobenius classical, or the embedding is Frobenius classical, and that's when it's nicest. And then you get the bound. So the bound depends on this Frobenius orders, and of course, the bound is smallest when the Frobenius orders are the classical order 0, 1 up to n minus 1. And you have this parameter n, and you can try to optimize n. If you plug in the classical Frobenius orders, you see that the optimal value is n is the square root of q. And if you still have to figure out what d is, if your linear system is non-special, so it has equality on the Riemann-Roch without the H1 term, then what you get is essentially the V-bound. So this is nicest when you have a special linear system and it's classical. So this way you can give a bound, a proof of the Hasse-Weil bound. For the proof of the Hasse-Weil bound, maybe you don't find a linear system over FQ that is classical, Frobenius classical, but you can find one over an extension, and proving the Weil bound for an extension is equivalent to proving the Weil bound on the ground over the ground field. So this way you get the Weil bound. You can get improvements when you're in a favorable situation. Like Gabor presented, there was lots of applications to maximal curves, and at this point I'd like to mention that one of the main contributors to that was Fernando Torres, who sadly passed away last year. There's also applications of these ideas to finite geometry, coding theory, and many other questions over finite. But I don't want to, this is a beautiful path if you want to have a hike on the beaten track. I recommend, I suggest starting with the original paper with Storr and going on to the many citations and explore. But I want to take a different direction, going back to my original result that was which is in Serge's notes, and some developments that happened from them that have not been as as thoroughly explored. And there are lots of open questions that I'm hoping that people will be inspired to work on. There's questions that at some point I looked at and I don't know the answer to. So I really would like to see if people can help me with that. Let's set some more notation. So you have a plane curve. So the whole setup in this talk in this particular situation, we're working with a plane curve. a plane curve of degree d bigger than 1, irreducible. So, well, absolutely irreducible. I'm going to denote by capital Phi the FQ Frobenius map. And so the curve has Frobenius orders u0 and u1 because n is 2. We say that the curve is Frobenius classical when u1 is equal to 1, and Frobenius non-classical if u1 is bigger than 1. When it's Frobenius non-classical, it means, it follows from the general definition, but you can take that as a definition if you like. Frobenius non-classical means that the Frobenius of P belongs to the tangent line to x at P for every point P. So for every point you have the P, you have the tangent line, and if phi of P is there, you say that the curve is Frobenius non-classical. Now the idea is, well, the Frobenius non-classical situation is a situation we perhaps can't handle so well. The Frobenius classical situation is the general situation where this condition here only happens to find for finitely many points, that the phi of P is in the tangent line. That will happen for finitely many points. And the nice thing about it, and that's why I titled my talk Counting Tangents, is you can count exactly how many points satisfy this with multiplicities. But the number of points that satisfy this condition is can be given exactly. So how do we do that? We write down this other polynomial here. So we start with an equation, say let's write an affine equation f of xy equals 0 for the curve x. And we write this other polynomial, xq minus x times the partial f x partial x plus yq minus y times partial f partial y. And so this is a polynomial. And this polynomial vanishes exactly at those points, because you can work out the equation of the tangent line for a plane curve. It's elementary geometry. So you plug in the Frobenius and you get that. So the curve is Frobenius non-classical if this polynomial vanishes identically, and it's Frobenius classical if on the curve if it doesn't. And one condition that will ensure that this polynomial does not vanish identity on the curve is degree less than P. So if the characteristic is big, things work very nicely. And now we can count the common intersection of these two curves, right? So if they don't have a component in common, and f is assumed irreducible, so that means that this other polynomial doesn't vanish on f, you can count just by Bezout. So you apply Bezout. So what is the degree of this polynomial? This degree of this polynomial is there's a q there, and then there's the derivatives of f, so it has degree d minus 1. So the degree of the second polynomial is q plus d minus 1. So you get the following fact, which is the main theorem. If a curve is Frobenius classical, the number of points on the curve is bounded by this quantity here. And then I have to explain what's happening. So this numerator here is what you get from Bezout, right? So is the intersection, the total intersection between those two equations here. The f and the other equation derived from f, which has this degree. Now, there's a local calculation that you have to do because there is a gain, there's a substantial gain in it, which is to show that the rational points, which, oh, by the way, the rational points are obviously here, right? Because if P is always in the tangent line at P. It's the embedded tangent line. So it's the line that goes through P and is tangent to the curve. And so if P is rational, P is in TPX. So phi of P, which is P, is also in TPX. So this second polynomial vanishes at the rational points, but you do a local calculation and you learn that it vanished doubly. The multiplicity of the rational points is 2. So you get this inequality here. And if you work a little, so if the curve is smooth, you know what the genus is in terms of the degree, and you get this other expression for the same bound. It turns out that this is the correct expression. So the equation in the middle, the inequality in the middle, doesn't assume that the curve is smooth. So you get a little bit better. If your curve is not smooth, you can take into account the singularities. So that's the theorem was in SAS nodes, except in SAS node he only deals with, he's interested in curves of genus 3, so he takes G equals 4, and the bound is n is less or equal to 2 cube plus 6. And so the bound is attained for many values of Q. You have to exclude characteristic 2 and characteristic 3 because you may have Frobenius non-classical curves. But if you exclude those, then you have this bound. And for several small values of Q, the first 6 or 7, I don't remember how many, you have equality. So it's very nice. Now, okay, so that's the theorem in SAS nodes, and there is a sketch of this proof there. And then we got generalized to curves in higher dimensional spaces by taking oscillating hyperplanes, etc. I don't want to talk about that. But so I want to explore this bound. I want to discuss, the sharpness of this bound and examples and so on. And I want to talk about a little bit about Frobenius non-classical curves as well. So that's let's go back to the previous slide. Is when this condition happens for all the points on the curve, and this polynomial then is identically 0 on the curve. Now here's an interesting thing, and this is special of plane curves that doesn't hold quite like that in higher dimensions. If this polynomial is identically 0 on the curve, and you plug in an x in FQ, then the first half vanishes, right? If x is rational, this first half of the equation vanishes. If you're assuming that everything is vanishing on the curve, the second half has to vanish as well, which is telling you that either y is also rational or the partial derivative with respect to y vanishes. So this is almost implies y is infinity. So in the case of Frobenius non-classical curves, having a rational x almost always implies that you have a rational y, which means what? So if that was true exactly for each rational x, there's d values of y that satisfies the equation because it's an equation of degree d. So on each vertical line, there's d points, except if the tangent is vertical. And so you should expect like dq points on your curve. And if you work it out, you get, this is a theorem that I proved with Abramovhefes a few years afterwards. You have this expression. So you get an exact expression for the number of rational points if the curve is smooth. You can also do it when the curves have what we called in the paper controlled singularity, so a very few singularities. So maybe not. Maybe it's just for smooth. Okay. I wrote smooth here, so I'll stick to smooth. So in the smooth case, you get an equality for the number of rational points. And notice that this is like d times q, whereas the bound here in the Frobenius classical case is d times q over 2, roughly. So Frobenius non-classical curves have many more points than Frobenius classical curves. So this is sort of a dichotomy, and it'd be interesting to know, for example, what are the smooth Frobenius non-classical curves? Because then you'd have some additional information, and you'd know what you can exclude to apply this bound. So here's the first little problem that I would like to raise is that question about Frobenius non-classical curves. Now, there's one thing that I know is that D is congruent to 1 mod P. And that holds for any non-classical curve. So one thing that if a curve is Frobenius non-classical, it forces it to be non-classical in the sense that the tangent line is always inflectional at every point. And this condition of being non-classical already implies that D is 1 mod P. But I don't think every D congruent to 1 mod P is going to be the degree of a Frobenius non-classical curve. Every D congruent to 1 mod P is the degree of a non-classical curve in the geometric sense, but not in the Frobenius non-classical sense. This is the first problem I wanted to raise. I want to mention a very cute result due to my former student Erivelto Borges, which is about the following question. Now we have this definition of Frobenius non-classical curves. Can it happen that the curve is Frobenius non-classical for two different finite fields? So if a curve is Frobenius non-classical for two different finite fields, you can take the F. So let's call FQ their common intersection. So you can write it as FQ to the n and FQ to the m with n equals to 1. When n is 2 and m is 1, you cannot get any, but if n is bigger than 2 and m is at least 1, there is a unique one. So there is a curve that is both Frobenius FQN and FQM Frobenius non-classical, and has this degree and this genus, and you can compute, of course, by, and the curve is singular. So the previous term does not directly apply, but you can compute the number of rational points over FQN, over FQM, and over FQ. And it's an interesting, very interesting curve. And I sort of must have forgotten this, but I got reminded myself by looking at Seth's book that the case Q equals 2, m equals 1, n equals 3 is an example in Seth's book. So it's a Frobenius non-classical curve over F2 and F8. And it's a maximal curve, I think, over F2 and F8. Now, so with the exception of Frobenius non-classical curves, we have this bound. And how sharp is this bound? That's one thing that I really would like to explore. So the first question that comes to mind is, what's the maximum number of points of a number of rational points of a plane curve of degree d less than q over fq? So I'm putting degree d less than q because as long as the degree is q or more, you can make the curve pass through all the points in P2. So there's nothing very interesting happening there. But when the degree is less than q, we don't have an answer to this question. There's been some work done recently by Faber and Grantham looking at number of points of curves of finite fields by gonality. And I'd really like to see a similar thing done for plane curves by degree. So if you could explore numerically when you know, what's the maximum number of points. So fix a d and a q. As long as they're sufficiently small, you can probably do a search and figure out what's the number of rational. And by the way, I'm always assuming implicitly that my curves are irreducible. Although my bound works for reducible curves that don't contain lines. So as long as every component is Frobenius classical and no component is a line, you can add the inequality together, and by convexity, the inequality holds even for reducible curves. Okay, so what do I know? So I'm going to switch to Q equals P, so the prime case, so I don't have to worry about non-classical curves for the moment, Frobenius non-classical curves. So in this interval, which, you know, in some sense is the longest interval, like it's a very long interval, it's most of the degrees for between P over 15 and P, I don't know any better bound for the number of points of a plane curve. When you get degree lower than P over 15, you can start using the Stov-Wöhler bound for other embeddings. So for example, you can use you start with a plane curve, you can embed it in P5 via the Veronese embedding, and then you get another bound, and this other bound becomes better than this bound when D is less than P over 15. So that's why I put this.
Sorry, Felipe, can I ask, I mean, when you speak about rational points, is it like of a smooth curve, or do you take a smooth model of it, or what is it exactly, rational points here?
It's so so the bound is for points in the smooth model. So you know you can overcount if you have say a point in the plane that is rational, but the tangents, but it's singular with tangents irrational slopes, then you're not going to count that point. There are variants, so you can account. You can try and account for the singular points, and you know I guess when the degree is small, there are not many, but when the degree is large, there can be a lot. But the theorem at stated is for the points in the non-singular model. But in fact, you know, the examples that I'm going to mention, they're all smooth curves. So somehow for the non-smooth curves, the number of points drops. Does that answer your question?
Yes, thanks.
Okay. So when is this bound attained? So the bound is n is less than or equal to g plus q minus 1 over 2. So when the degree is p minus 1, it's easy. It's just take x to the p minus 1 plus y to the p minus 1 equal to what? To 2, right? That's going to be all the points with non-zero coordinates are going to be in there. So that's easy. We have some examples with these co-authors of curves of this degree when p minus 1 factors like this. So this is p minus 1 minus 2k. So the degree is p minus 1 minus 2k, where k is a factor of p minus 1. So you get a bunch of examples of degrees that are sort of on the upper half of this interval. So they're both bigger than p minus 1 over 2. So the smallest thing that you can put in is k is p minus 1 over 2. The biggest is k is p minus 1. Yeah. You can write down all the possibilities, but they're, you know, they tend to be in the upper half of this. I think you can do p minus 1 over 3 and get 1/3 p minus 1 over 3. With Carlin, we found some examples of degree p minus 3 over 2 when this number is even. So p has to be 3 mod 4. And recently, Borges, Cook, and Coutinho found some examples with those degrees, again, if they're even. The degree has to be even because otherwise the right-hand side of the inequality is not an integer, so you improve a little bit, right? So if you really want equality on this bound without rounding to the nearest integer, you're going to have to take the even. So those are the only examples I know of equality in the bound, and I suspect there should be many more, but I have no idea. So any other cases where this bound is shown? This is the other question I'd like to pose to all of you. And one thing I want to remark is that very often in problems coming from other contexts without sort of, you know, studying curves of finite fields for their own reason, if you're working on the problem coming from somewhere else, take coding theory or problems over finite fields and so on, you are often given an equation. And it's usually an equation into variables. So this situation of plane curves is very, very relevant for a number of applications. So, you know, AQ is all very well, but, you know, you never write a general curve in genus G. So this should be explored more, I think. Okay, so now I want to move on to surfaces. So we have the Weil bound. We also have the Lie bound. We have the Weil conjectures. We can bound a number of rational points on surfaces. We don't have the theory that we have for curves, right? You know, there's very few results of, you know, of the type of in Serre's book, you know, the same spirit as Serre's book for surfaces. But, you know, I can generalize my old results for surfaces, but no beaten track here. So this is a situation, I can prove a theorem for surfaces in P3, which is going to be very similar to my old result for plane curves, but I'll really love to be able to generalize this theorem to to surfaces embedded in a higher dimensional projective spaces, or even if you start with a surface in P3, what can you do? What else can you do? What other bounds can you get on the same spirit? And I don't know how to do that. But let me tell you about this particular result. So if I'm going to assume that you have a smooth surface of P3 of degree D over FQ. I'm going to assume that Q is prime and that D is less than Q. So I'm doing that to be safe from bad geometry. So there's not going to be any bad geometric things happening. And I get a bound which is kind of looks like the previous bound is D plus Q minus 1. So those two factors already occurred for plane curves. There's an additional factor. You can't expect it to be linear in Q, right? You expect the number of points on a surface, you expect to be of the order of Q squared. So not surprising there's another factor. There is a thing that you divide by. And then there's a very new thing that didn't appear in the previous case, which is this extra term, which is M is the number of lines contained in S. Number of lines defined over FQ. And you have to add, and M times Q plus 1 is the number of points on those lines. Or this is an upper bound for the number of points on those lines. And we'll see in the proof, so I'm going to give a sketch of the proof, we'll see how this term appears. And of course, there is no analog of that for situation in curves. But and if you use the old bound of Salmon for the number of points or number of lines contained in the surface, you get this bound here, only in terms of only D and Q. And let me just check something here. This bound is better than what you get from Deligne when D is bigger than something like square root of Q over 3. So in this range, this bound here is better than what you get from them. So it's an interesting bound. I have no idea how sharp it is. I have a couple of examples. So if you look, the paper where I proved this is quite old. It's in a contemporary mathematics volume about 20 years ago, maybe 15. I don't remember. But you find it. It's called surfaces over finite fields. Surfaces in P3 over finite fields, and I have a couple examples where the bound is attained, but I don't have a sense for how often this bound is attained, for which degrees this bound is attained, and all of that. So, and again, can this be extended to higher dimensions or higher codimensions? So I have very little idea of how this would go. I have some dreams, but not any concrete ideas. I'll tell you about my dreams in a moment. But let me tell you a little bit about the proof of this theorem. So again, you're going to count. So you could be tempted to count the number of points P for which phi of P is in the tangent plane to X at P, but that's not good enough because the tangent plane is too big. So the intersection of the tangent plane with the surface, so if you have a surface and you intersect it with the tangent plane, you typically get a curve like this, right? So the intersection of the surface with the tangent plane is a curve. It's a curve that is singular at P. So this is the surface and the tangent plane. And if you intersect the surface, my drawing is terrible. That's how it is. If you intersect the surface with the tangent plane at P, you have a curve that is singular at P. Typically, what you see is a nodal singularity, and it has two tangents. And these two lines, which are the tangents at P to S intersect TPS, are called the asymptotic lines to S at P. These can also be characterized as lines intersecting S at P with multiplicity 3 or more, generically 3. So now you have two lines and a pair of lines, and the condition that phi of p is in this pair of lines gives you two additional conditions on p. So you expect a finite set, and in fact you can work out what it is. So if you take a homogeneous equation, so now I take f to be a homogeneous equation defining the surface, and I take this expression here, which is very similar to what I had before, is the partial derivatives of f at xi times xi to the q, and then I take a sort of a quadratic term, which is the second partials multiplied by xi to the q or xj to the q. This system of equations define precisely this set. And then we can look at the numerator here. So the three terms that the numerator of this part of the equality are the degrees of these three equations. So I'm looking at a system of three equations in P3. So I can apply Bezout, and I say, well, the total number of points is this product. The rational points come with multiplicity 6. This is a local calculation that you have to do. But it's doable. Is a little bit of local algebraic geometry. And so you get the 6 here, which makes the bound better. If there wasn't the 6, the bound would be essentially useless. The 6 makes it very nice. So that's almost the proof, except this equation here. So this is the proof if the system of equations defines a zero-dimensional set. So if the intersection is such that it's zero-dimensional, then you have you can apply Bezout and you're done. But it can happen that this system of equations have one-dimensional components. It's not the whole surface that can be proved that will follow from the condition that d is less than q and q is prime. So that's easy to say that it's not everything, but it could have one-dimensional components, and it does when the surface contains lines. This you cannot avoid. So the surface contains a line. The line is a component of this intersection, and so we have to work a little bit and prove that the one-dimensional components of this intersection are precisely the lines. So once you do that, you get this. Okay, so I want to make one further comment about this result, having to do with this appearance of this one-dimensional component. So the Ling bound for maybe is S. So let's call it S. Is q squared plus 1 plus b2q. So actually, what you have is that this is equal to q squared plus 1 plus sum of I from 1 to b2. So I'm assuming it's a smooth surface in P3. So there's no H1 or H3 term in the étale cohomology. So you're just looking at H0, H2, and H4. So you get this, and by the Riemann hypothesis, this alpha I. So the bound is given by that, and B2 is the second Betti number, is the number of eigenvalues of Frobenius on H2. And because of the Riemann hypothesis, you get this. And just like in the case of curves, if you have low defect, if you have a surface that gets close to this bound, that is just equals the bound, or the bound minus 1 or the bound minus 2, what you can prove is that many of these alpha i's are equal to q. So almost equality if alpha I is many alpha i's are equal to q. Now, the number of alpha i's that are equal to q is, by the Tate conjecture, I guess it's not known, is the rank of the Nernst-Overi group, the Picard number of S, right? So this is the Tate conjecture. So a surface having many points should be explained by it having many curves that you don't normally expect. And my theorem there shows that if the bound gets worse, so that you get a bigger bound, when you get lines that you don't necessarily expect, right? So this term here appears when you have lines that you don't expect. So you can dream, and I've dreamt of this many times, but I haven't managed to make it become a reality, that a proof of dare say the Weil conjectures for surfaces, or maybe something approaching that, or something like that, would, in the process, write down some equations for which the one-dimensional components give you elements of the Nernst-Overi group. And so in this way, so maybe it's a bad thing that I can only imagine proving the Ling bound via this method if I can prove the Tate conjecture at the same time. So maybe this is a bit too optimistic, but who knows, right? And then certainly anything towards that would be interesting. So so there's one case that I sort of played around with, which is not too bad, which is the surfaces in P4. You can then ask the condition P Frobenius of P in TPX. Now that makes sense. That makes sense, it gives you a zero-dimensional set. So this is a one other case where you can actually count. So if you have S in P4, or X in P4, surface, and then you can look at that, and that might lead to something like that. I don't remember correctly. I think so you have the surface in P4, you're assuming that it's not contained in a P3. So it usually doesn't contain any plane curves, but if you have a plane curve inside the surface, so a curve that is inside the surface in P4, but the curve itself is contained in a plane, then you get one-dimensional components on the set. So that's the kind of situation that you're going to get. So this one, again, it sort of leads to the sort of same situation. I haven't actually I don't have a complete proof of the situation. Before I have some ideas, but that's pretty much as far as I got with this. And so I think I'm going to leave you guys with the thought of maybe you should work on this as well, or the other problems on plane curves, which might be more approachable. So thank you very much.
Thank you very much for this inspiring talk. Are there any questions from the audience? I was just wondering, the P2 that you mentioned, the second Betti number, what is it exactly, and how does it compare to the bound that you showed?
The Betti number is the cubic polynomial in D, is D cubed minus 4D squared plus 6D minus 2. So it says, so the bound is something like Q squared plus D cubed Q. Those are the main terms. Yeah. But my bound is something like dq squared over 6 plus some terms that involve d and q.
Yeah.
So you really need to have d quite big so that my bound beats the D.
Okay, thanks. And so your question about plane curves. So basically, you're looking at curves which have a simple G2D, then like a linear system G2D.
Yeah.
So one half is birational. So would it be interesting? We have already been talking about counting points for curves with a given gonality, and now you have this. So how far is this reasonable to push this question, where you just count the maximum number of points on curves with?
I'll be very interested to see the data. I don't know. I mean, I don't really have. I haven't done a numerical exploration of this, so I don't have any data. I have those examples that I constructed. And me and other people have constructed by hand.
So like on P1 cross P1 with a given bi degree, has anyone worked?
Well, you can also do that. Yes, you can do things like that. This you can view it as a curve in P3 and apply Felipe Voloch to that, or you can work on it by itself. So there is a recent result. There's a thesis by Jade Nardi in France, where she looked at curves in Hisenbrook surfaces. And so P1 cross P1 is an example of that. And she noticed, so the surface has two different affine shards, two different natural affine shards. And you can apply my method to both charts, and you get different functions.
Okay.
And what you notice is that you cannot have both of them being Frobenius non-classical. So you get, so you're going to get a bound no matter what, because one of them is going to work.
Okay.
The bounds are not great, unfortunately, but the idea is nice. So if that could work more often and in other situations, or maybe that particular bounds could be refined, then you could get something for P1 cross P1, for example. You can, if P1 cross P1 is something like, you do it, you have the A1 with XY, and then you have the other one with 1 over X and 1 over Y. And those, yeah.
Okay, thanks. There's a question by Christophe.
Yeah.
Where is that? Yes.
Yeah, I mean, first I wanted to say maybe Jade is not here with us tonight because she's celebrating that she got a permanent position at CNRS just today. So
Congratulations to her.
Maybe right. Yeah, I wanted to know, I mean, I'm really glad that you mentioned plane curves. I mean, because I think that it is indeed an important topic that wasn't mentioned until now somehow, and the number of points on them. And I'm just quite confused already always with this object because I haven't really worked with them, but how your results like articulate with the one of HOMA?
HOMA?
Yeah.
Yeah, so HOMA is bounds for the degree is like Q minus 1, Q minus 2. I mean, the Scali bounds that HOMA proved, these are good when D is very close to P minus 1.
Okay.
And then my bound kind of takes over a bit earlier. But the proof of this Scali bound, some cases uses this bound. So they are related.
I would need a line with the D and the Q to see exactly.
Yeah. You have to put
results.
But
okay.
So I think this Scali bound is for all plane curves, even if they are not irreducible. So you'll be allowing everything, just equations f of xy equals 0.
No line inside, I think.
No line, maybe no line. Yeah.
Okay. So I mean, it's not in the same range as you are considering now. That's what you say.
Yeah.
Okay. Thanks.
Thank you. Are there other questions? If not, I don't see anything on Zulip. Then let's thank Felipe again for the nice talk. And then, let's call it a night or a morning, wherever you are.
If anybody wants to continue chatting, I'll stay here for a bit longer. It's 9 a.m. Not quite 9 a.m. for me, so I'm happy. But I will understand if the Europeans go to bed. And if the Americans have things to do.